Matrix displacement method, frame analysis. In the previous lectures, we defined a beam element with 4 degrees of freedom, 2 vertical displacements, and 2 rotations. See Lecture SA 47. We also defined a truss element with 2 degrees of freedom, 2 axial displacements. See Lecture SA 48. If we combine these two elements, we get a beam column element with 6 degrees of freedom. In this lecture, we want to come up with a matrix formulation for the beam column element and to show how it can be used to analyze frame structures. Given that our element has 6 degrees of freedom, we can define 6 member end forces. We label them F1 through F6. From previous lectures, we know that the force and displacement vectors are related to each other via a member stiffness matrix. This is the member force vector. This is the displacement vector. And this is the stiffness matrix, all specified in a local coordinate system. We can define the elements of this matrix by superimposing the truss and the beam member stiffness matrices. Here is the beam stiffness matrix given in the local coordinate system. See Lecture SA 47 for details. We are going to turn this matrix into a 6 by 6 matrix. Why? Because the beam column element that we wish to define has 6 degrees of freedom. To do so, we add 2 rows and 2 columns of zeros to the matrix, like this. Let's refer to this matrix as KB. The truss stiffness matrix in the local coordinate system is. We turn this into a 6 by 6 matrix by adding to it 4 rows and 4 columns of zeros, like this. Let's refer to this matrix as KT. If we add KT to KB, we get the member stiffness matrix for our beam column element. Denoting this matrix as K, we can express the relationship between the force vector and the displacement vector in matrix form. But before we can use K to set up system stiffness matrices, we need to transform it from the local to the global coordinate system. Here is the beam column element in the local coordinate system. Let's rotate it by angle theta and situate it in the global coordinate system. Member end displacements in the global coordinate system can be shown like this. We now need to express each displacement in the local system in terms of the displacements in the global system. Let's start with D4. It can be defined in terms of global D4 and D5. The sum of the projection of the global displacements onto the local x-axis gives us D4, so we can write. Similarly, D5 in the local system can be expressed in terms of D4 and D5 in the global system. No special transformation is needed for D6. It equals global D6. This is the case since they both represent rotation around the z-axis. Note that the rotation of the xy plane by angle theta does not change the orientation of the z-axis. It remains perpendicular to that plane. That is why D6 in the local coordinate system is the same as D6 in the global coordinate system. We can write D1, D2, and D3 in a similar manner. This gives us a total of 6 equations. Writing them in matrix form, we get. We call this displacement transformation matrix T. We can obtain a similar matrix for force transformation. Here are the member forces in the local coordinate system. Here they are in the global coordinate system. Let's define global F4 in terms of local forces. This can be done by adding the projection of local F4 and F5 onto the global F4 axis. So we can write F5 can be defined in a similar manner. As in the case of displacement, global F6 equals local F6, since they both represent bending moment about the z-axis. Writing a similar set of equations for the forces at the other end of the element, we get these equations can be expressed in matrix form, like this. Let's refer to this as force transformation matrix Q. Now we are ready to come up with member stiffness matrix in the global coordinate system. We start by writing the member equations in the local coordinate system. That is, F equals K times D. Pre-multiply both sides of the equation by Q. Remember that Q is our force transformation matrix. The left-hand side of this equation equals F, since we know the uppercase F is the force vector in the global coordinate system, and the lowercase f is the same force vector in the local coordinate system. Further, since the lowercase d equals t times the uppercase D, we can write, given that F and D are given in the global coordinate system, then Q times K times T must be member stiffness matrix also in the global coordinate system. Here is Q, here is K, and here is T. Multiplying Q by K by T, we get where alpha equals EA over L. Beta equals EI over L cubed. C is cosine theta, and S is sine theta. Here, E is modulus of elasticity of the material, I is moment of inertia about the axis of bending, and A is cross-sectional area of the element. This is the global stiffness matrix for our beam column element. We are going to use it to assemble system stiffness matrices when analyzing indeterminate frame structures. Let's see how. Suppose we want to analyze this indeterminate frame. The frame has two members, AB and BC. Here are its section and material properties. We start by writing the stiffness matrix for each member. For AB, we have here alpha equals 100,000. Beta is 6. C is 0 and S is 1. Substituting these values in the matrix, we get for BC, alpha is 125,000, beta is 11.72, C equals 1, and S is 0. Substituting these values in the matrix, we get now we are ready to assemble the system stiffness matrix. The frame has 4 degrees of freedom. There is a rotation at joint A, a horizontal displacement at B, a vertical displacement at B, and a rotation at B. We label them D1 through D4. There is also a corresponding force vector. We label the forces F1 through F4. The relationship between the force vector and the displacement vector can be written this way. The force vector is that of applied joint loads. In this case, there are only 2 non-zero forces. Let's determine the elements of the system stiffness matrix. We do this by adding related elements from the member stiffness matrices. Let's keep the numbering system for members AB and BC in mind. Here are the numbers for AB, and here they are for BC. K11 of the system is the same as K33 of member AB. K12 of the system is the same as K34 of AB. K13 is the same as K35 of AB. K14 is K36 of AB. K22 of the system is the same as K44 of AB plus K11 of BC. And so on. Since we already have calculated the coefficients of the member stiffness matrices, we can easily determine the system coefficients. Here they are. So the linear system of equations that we need to solve is this. The unknowns are the degrees of freedom of the structure. Solving the equations, using, say, the Gaussian elimination method, we get these values. We can then use the computed displacements to write the displacement vector for each member. For member AB, we get, and for BC, we have, knowing the stiffness matrix and the displacement vector for each member, we can calculate its member end forces. For AB, we get, here are the forces shown graphically. For member BC, the end forces are Now, we can easily determine the support reactions for the indeterminate frame. By the way, knowing the member end forces, we can easily draw the shear and moment diagrams for the entire frame. We will examine the analysis of frames subjected to member loads in a future lecture.